Hello, everyone. Welcome to our last program of Wednesday Astronomy Days. I'm Carrie. I'm an educator here at the museum, and I am so glad you're joining us this evening for a really, really cool program. So our program is Getting from Here to There, and I have an icebreaker question for you. If you could go anywhere in the universe, where would you go? So put that in the chat. And while you're answering that question, I'm going to go through a quick Zoom tutorial so we have the best possible viewing experience. First, actually, I would say, is our program going to be captioned tonight? I did not see a transcriber, so I will, we can use the automatic Zoom captions, but I don't think have live captions for this program. So we will skip that. But we do want you to have the best view possible. So if you go up to view options, make sure you're in side-by-side mode. That just makes sure that our videos are next to the slide, so it's not obscuring your view of that. And also over here, you can see, you can move that bar back and forth so you can see us really large or the presentation really large, just whatever you like to see. Lastly, we totally want to hear from you in the chat. We love hearing your questions and your comments. So make sure you put those in the chat. Just remember, please stay on topic and please be kind and respectful to the speaker and each other in the chat. So be a good digital citizen. With that, I'm going to introduce our speaker. So Matt Funk is a NASA JPL Solar System Ambassador and has worked with the museum for many years with Astronomy Days. So welcome, Matt, take it away.
Well, thank you very much, Carrie. As she said, I'm a solar system ambassador working for Jet Propulsion Labs because honestly, we're always doing cool stuff in space, but it can be very hard to know about it. Basically, Jet Propulsion Lab set up this as an outreach effort to get volunteer educators trained on information to learn about what we're doing in space and how it's done. And basically, it's our job to go to schools and libraries and museum events like this to talk to people. And I love doing Astronomy Days because the people here always are so engaged. They want to learn about this stuff. And they have the best questions, stuff I've never heard before. So I'm really eager to jump right in. Okay, my topic is going to be getting from here to there. Let me see if I can hide this. I'm trying to hide the controls here. There we go. This is a picture of the solar system highway. It's more of an artistic depiction than anything else. It was an attempt to show how you can use different planets to get yourself around in the solar system. And it's sort of indicative of the weird twisty turny nature of everything, which can kind of make it really confusing, honestly. You might start to wonder, how on earth can they figure out where to send a rocket so that hopefully the rocket and its target are in the same place at the same time? How do they figure out how to get different places anyway? And hopefully I can remove a little bit of that mystery for you. As always, feel free to interrupt with questions or whatever. I'll try to do the best I can to answer them. And I'll be honest, if I don't know, I might have to refer you to something else. But hopefully this will give you a little bit more insight into how we get around in the solar system. Basically, the things you need to know boil down to 3 rules that a fellow by the name of Isaac Newton came up with. Isaac Newton was a very, very clever individual. And he was clever because he figured out that things weren't quite what people thought at the time for more than 1,000 years before he wrote his stuff. A guy named Aristotle had worked out what he thought the rules of motion were. And in his rules, everything tries to come to a stop, which squares with our experience. And the reason things fall down is because like things get attracted to like things. And if everything is made out of earth, air, fire, and water, then the things that are mostly earth will be attracted to earth. And it worked well enough to predict general things about how how things move. But Isaac Newton nailed it down to a way that could be described precisely and mathematically. And I'm going to give you sort of simple versions of his 3 rules. Rule number 1 is that things that aren't moving won't move by themselves. And things that are moving can't change their direction or their speed by themselves. Now that was big, right? Like I said, up until that point, people thought everything just kind of comes to a stop all by itself, because that's what happens in most of our experience. But what Isaac Newton realized was that things come to a stop in our experience because other things are always getting in their way. So he changed that to say, no, things will keep moving unless something actually acts on them to stop them. In space, it turns out that there's very, very little friction at all. But let's see if I can hide this again. Here we go. There's very, very, I'm sorry.
So Matt, we still have these bars obscuring our view.
You do.
Miranda, can you quickly tell us how to make that stop? Oh, okay. Okay, so we'll just live with it. Okay.
Just try to live with it? Okay.
Okay, thanks.
There's very little friction, but there is gravity, and I'll get into that in a bit. That tends to be what changes our direction the most. Rule number 2 is that acceleration, what we call acceleration, is a change in speed or direction. So you can keep the same speed, but if you change direction, that's still considered acceleration from a physics point of view. And the amount of change depends on the amount of force. That's really handy. If you want to change the direction or the speed twice as much, you need to put in twice as much force. And it's really straightforward, honestly. It's simplified a whole lot of things. And with rule number 3, you've probably heard something like this before. Forces come in pairs. For every push in one direction, there's an equal push in the opposite direction. You may have heard it fancily phrased as, for every action, there's an equal and opposite reaction. Now, this really helps us with rockets, obviously, because we need something to push or pull the rocket to change its path and get it to go in the direction we want it to go. But obviously, one of the questions I get a lot is, how do rockets work in space when there's nothing to push against? And I think that's a valid question. You can kind of picture an airplane as it goes through the air. It's got its propeller turning, and you can picture the propeller pushing against the air to pull itself forward, or a boat shoving its screws through the water and pushing against the water to shove itself along. What can a rocket possibly push against? There's nothing in space. Well, it's kind of weird to think about, but the rocket actually pushes against its propellant. I'll try to show you a little bit of an illustration to help with that. This here, I don't know if you still have these little scooters in gym class, but we used to sit on them all the time and scoot around like crazy. Anyway, and what she's holding there is a medicine ball. It's a very heavy ball, about 10 pounds weight. If she throws that ball, she will tend to scoot in the opposite direction. That's pretty straightforward. If she has a lot of bean bags that are equal to the weight of the ball, and she throws them off one at a time, she'll scoot backward with each one that she throws, and she'll actually go faster than she would have with the medicine ball, because every time she sheds weight, she's pushing less weight with the bean bag, if that makes any sense. She's reacting against less weight. In a rocket, what you have with a rocket engine is this big bell out the back end. You've probably seen it. And when the fuel and oxidizer meet at the top of the inside of the bell, they expand like crazy. It's an explosion, right? The bell's job is to get all of the particles in that combined mixture to bounce off the walls and shoot out in the same direction. They all shoot out backwards, so the rocket goes forwards. It's like shooting out millions and millions and millions of tiny cannonballs or tiny beanbags out the back of your ship. So basically the rocket recoils in the opposite direction, and it pushes against the propellant to shove itself in the back. I have a little, oh, come on. Focus keeps going away from my meeting here. I have a little Kerbal Space Program screenshot here to try to show that a little bit. The propellant doesn't push against anything but the rocket itself. And that's kind of a tricky point. But if you can wrap your head around that, you can understand why rockets fly. Now, I mentioned before that if you leave things to themselves, they fly in a straight line, right? Or actually, Isaac Newton said that. I can't take credit. But rockets, after they get into orbit, shut off their engines, so there's no rocket propulsion pushing them in any direction, and they manage to move in a circle. Now, can you come up with a reason why that path would be bent into a circle? I don't know if anybody's saying anything in chat, but I'll ruin the spoil. I'll spoil it.
Ruxin says gravity.
Gravity, yes, absolutely. That's absolutely the right answer. Yep, gravity. Some people think that when you get into the space shuttle or the ISS or something in orbit, that you have escaped the Earth's gravity, and that's not quite true. Honestly, if you were to stop the ISS somehow and magically suspend it where it is, you would be pulled down towards the center of the Earth with almost as much force as you would feel on the surface of the Earth. It's just that the ISS or the shuttle or whatever we're talking about is moving sideways, right? So as it falls down, it shoots out a little bit sideways, and it manages to go sideways fast enough that it misses the Earth. The Earth curves away from it before it can hit. That's really kind of a tricky point. So I'll bring up another illustration. This actually showed up in one of Isaac Newton's books to try to illustrate what he was talking about. He came up with the idea of an orbit. See, he decided you could put a cannon on the top of a very tall mountain, and if you shot it with just a little bit of force, here with A, it would just kind of bloop out at the bottom of the cannon and hit the Earth. Right? If you shot it with a little more force, like in B, the Earth would curve away from it a little bit, and it would go further than just the extra force because it had further to go before it hit the ground. If you balance things just right, and you get between get going sideways at the same speed that the Earth curves away, you end up in orbit, and you never fall down. You keep going around and around and around. If you give it a little bit more force than that, you end up following path D that swings out further away from the Earth than the cannon before swinging back in. And it keeps swinging back and forth like that. Give it even more force than that. There's a certain minimum amount of speed where you can fly away and never come back, because the Earth's gravity keeps getting weaker and weaker and weaker as you fly away, and it's never strong enough to actually reverse your direction and pull you back in. That minimum speed is what we call escape velocity. You have to be going escape velocity or faster if you want to start flying to other planets besides the Earth.
So we have a question.
Sure.
So People is asking, is the zero gravity feeling of orbit, is that like perpetual free fall?
Yes, it absolutely is. If you were in an elevator and somehow dropped in the elevator, you and everything inside the elevator would float around exactly as you would inside the ISS or inside the shuttle, and at least until you hit the ground. Right? And for the same reason, because everything is falling, and you're all falling at the same speed. So if you want to talk to people who try to get technical about this sort of thing, and I run into a lot of them, they will say that you shouldn't call orbit zero gravity. You should call it microgravity or something that still lets people know there's still gravity involved. It's changing our path. We wouldn't stay anywhere near the Earth if it weren't for gravity. It's just that you don't feel the effects of gravity. And that's kind of subtle, but it makes all the difference. That's why people bounce around inside their rocket cabins and so forth. Okay, moving on from Isaac Newton's little diagram here, I'm going to show you basically a flight from Earth to Mars and how that works. You may remember part D, which has a sort of an oval path that scoots out far away from the Earth and then scoots back in. Here I have a picture of the sun at the center, the orbit of the Earth in blue, and the orbit of Mars in red. Now, the path that the rocket has to take to get from the Earth's orbit to Mars' orbit is that half a white oval that you see there. And what you need to do is give yourself that extra little boost of speed so that you're no longer in a roughly circular orbit around them. You actually swing out far enough to hit Mars. And of course, you time things so that when you get out to Mars's orbit, Mars is going to be at that same point in its orbit as your rocket. Right? And that happens roughly every 1.5 years, 2 years, and it takes about 9 months to make that half an orbit. That can change a lot because Mars' orbit, as it turns out, is significantly oval, and sometimes it's a lot closer to us than others. And when I say 7 to 9 months, that represents the minimum energy orbit, this half an oval orbit. If you can keep firing your rockets at some point, you can cut some of that travel time down. And NASA's doing some work with new rocket technologies to cut that down. Some of the nuclear rockets that they're looking at can cut it down instead of from several months to several weeks. And that's really promising. All that's very experimental, though. So anyway, the reason it continues to follow these curved paths, though, we've left the Earth, so we're no longer worried about the gravity of the Earth. We're going at escape velocity away from the Earth. Do you know why these paths of these rockets are still curved?
Anybody have any answers?
Anybody?
Anybody out there? Let's see.
No, it's a little tricky.
Bill says gravity of sun.
Yes, absolutely. Gravity. It's
All right,
the gravity
Bill,
of the sun.
you get the gold medal.
Yes, that's tricky, but yes, that's what keeps the planets in curved paths, and it's what keeps the rocket in a curved path. It takes a lot of rocket power to break the pull of the sun, and to be honest with you, that's beyond our technology right now. If we want to send something out of the solar system, we have to cheat a little bit. I'm going to get into that. Right? When you're talking about objects flying around planets or a sun or anything that exerts gravity, there are two kinds of energy you need to think about. The kinetic energy, which is the energy involved in motion, and the gravitational potential energy, which is how much energy an object has just because there's gravity pulling on it. And the further you pull it away from the gravity, the more gravitational potential energy it has. Now, if those two things, the kinetic energy and the gravitational energy, can change as an object flies around, but as long as you don't turn on the rockets or anything, they always sum to the same amount. The amount of energy is always going to be constant. So if we draw a picture around Jupiter, which is the planet we most often use to break free of the solar system, it turns out that Jupiter is about as far as we can get with current rocket technology. I'm going to draw a circle around Jupiter that shows a region where the gravitational potential energy is the same. So everywhere equally distant away from Jupiter. In real life, it'd be a sphere, but I've got a flat drawing here, so I have to make it a circle. If something fell in to Jupiter's orbit, you'd expect that at the points in the circle, it would have the same gravitational energy. And there's no rockets being turned on or anything, so it should have the same kinetic energy at those points too. How is it that Jupiter manages to sling things out of the solar system? How shouldn't things leave at the same speed at which they come in? And the secret answer to that, the whole thing that makes the slingshot work, is that you're right if we're looking at things from Jupiter's point of view, but Jupiter is moving. Jupiter's moving around the sun. I'm going to point in that direction. Basically, Jupiter's orbit is huge, and on this scale, we can just pretend that Jupiter's moving in a straight line. If you end up leaving in the same direction that Jupiter is moving, what it looks like from the sun's point of view is that your spacecraft picked up speed and Jupiter lost a little bit of speed. Now, Jupiter's way, 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 way bigger than the spacecraft. So the amount of speed it loses is tiny compared to the amount of speed that the spacecraft gains. But that's essentially how the slingshot effect works, is it steals some of the planet's energy of motion around the sun for itself. And of course, since everything has to balance out, the planet loses some in the equation. Back in the 1970s, when the Voyager space probes were visiting Jupiter, and we were planning to sling them free of the solar system, people figured this out, and there were picket signs of people outside the Capitol saying preserve Jupiter's orbit and stuff like that. It turned out that Jupiter slowed down something on the effect of a trillionth of a centimeter every million years or something. It's very difficult to calculate how tiny the difference in Jupiter's motion is. But, honestly, people who don't bother to do the math can get themselves scared if they hear that something's going to be different. and if they don't understand, you can't blame them for reacting a little bit like, wait, what are we messing with here? It turns out that there's a balance to this too, because Jupiter, if we fly out opposite Jupiter's motion, we slow the spacecraft down instead of speeding it up. And that allows it to fall in towards the sun. This kind of maneuver we will use sometimes if we're sending things towards Mercury. It turns out that it uses less fuel to fly out to Jupiter, have Jupiter slow it down, and have it fall into Mercury than flying to Mercury directly.
So cool. So Matt, I think we have got a consensus on how to get rid of the bars.
Yep.
So it has to do with when we had your settings so optimized for video sharing. So if you stop sharing and reshare and don't hit that, and then when you do have your video, you'll just stop sharing, so you'll just have to like go back and forth with your sharing. Does that make sense? So if you stop sharing now, stop sharing because what's happening, these bars are really obscuring your slides. Okay. So if you share now, but don't hit optimize for video sharing, don't check that box this time. That box has not been checked. Oh, that box wasn't checked? Okay. No, well, try resharing and maybe it'll be
okay.
Oh.
Let me turn off the
I don't see any bars, so this is an improvement.
You don't? Okay.
All right.
Okay, well, give it a shot. Awesome. If the slingshot effect is still kind of confusing to you, I have a little bit of an illustration that might help. Imagine, if you will, that your spacecraft is a tennis ball, and you have a really, really massive train, and that train's going to represent Jupiter. And you want to change the direction in which you throw the ball, and you want to change its speed, ideally. Well, what happens depends on whether you go with or against the train's direction of motion. If we have our little picture here, and we'll say she's just off the tracks, so she's not going to get hit by the train, obviously. And she throws her little tennis ball at the train at 30 miles an hour. From the train's point of view, that ball is approaching at 30 miles an hour. I'm sorry, at 330 miles an hour, I should say, right? If you add those two together, you get 330. So from the train's point of view, that ball also has to leave at 330 miles an hour. That tennis ball isn't going to slow down that train a whole heck of a lot. So what that means is that the ball flies back at 630 miles an hour. I don't recommend doing this exactly, but and I don't know how exactly to work out an experiment you could do at home to try to verify this to yourself. But if you take a small object and fling it at a large object that's coming in your direction, the small object will fly back at you faster than it went, from your point of view, than it went in. So this makes the same point that I just make. From the train's point of view, the ball approached at 330 miles an hour and it left at 330 miles an hour. If you want to slow the ball down, you can throw it at the train as it's leaving. Okay, let's say we've got a really good pitcher here who can throw at 350 miles an hour. From the train's point of view, because the ball isn't going to change its speed very much at all, that ball comes in at 50 miles an hour and leaves at 50 miles an hour. But what it looks like from the pitcher's point of view is that when the ball bounces off the back of the train, it continues to follow the train, but more slowly than it did when she threw it. So it will continue to follow the train from her point of view at 250 miles an hour. Slower than the ball and the train exchange energy. And from the train's point of view, the ball's speed doesn't change before it hits and after it hits. It changes direction, but not speed. From the point of view of the stationary pitcher, obviously, the ball's speed changes a whole lot. Okay, once we get to our destination, wherever that happens to be, we have to slow down, because again, you'll have the same amount of kinetic and gravitational energy leaving as you did coming in to the planet. From the planet's point of view, means that if you don't slow down, you're going to fly right on by. The most obvious way to slow down is to use rockets again. Instead of pointing them in a particular direction and keeping them on to speed up, if you point the rocket backwards and fire in that direction, you slow down. And this is a picture of Cassini back in 2004, slowing into orbit around Saturn. Cassini spent several years in orbit around Saturn and found all kinds of neat stuff there, but that's somebody else's presentation and I'm not going to ruin it. More recently, we have used a technique called aerobraking. In planets with atmospheres, you can actually use the atmosphere to slow down. You exchange energy with the atmosphere. Most of that energy, believe it or not, is not friction. It's in changing the direction that the particles of the atmosphere have. That's a very, very subtle point. But you can see here with Mars Global Surveyor, for example, it took several dips into Mars's atmosphere, slowing down a little bit more each time, that eventually caused it to settle into Martian orbit. If you want to land on the surface, that's going to be challenging again. Mars, in this respect, is a little bit of a troublemaker. I know Venus is our big focus, and landing on Venus is actually easy. Staying operative on Venus is hard, but landing on Venus is easy because it has this nice thick atmosphere, and we know how to make parachutes work. We know how to several ways of slowing you down in an atmosphere. Venus's atmosphere is, if I'm remembering correctly, about 90 times thicker than Earth's. So it's got plenty of stuff to slow you down. Mars is at a weird balancing point where if you bring parachutes, it'll slow you down, but not enough to make you land gently. And if you bring rockets, you'll have to bring a whole lot of rocket power to be able to slow yourself down all the way down to the surface. So you're going to have to use both. Unlike an airless world where you can concentrate only on rockets, or a world like Venus where you can or Earth where you can concentrate only on parachutes, with Mars you have to be good at both, and that makes it a whole lot more challenging to land on. If I can get this this video to work here, this is an excellent video of the Curiosity rover when we got it to Mars. We used an absolutely insane way to get it to land on Mars gently. It's what you'll see here mostly is called a sky crane, and it's actually a hovering platform. It uses rockets to hover and lower the rocket gently to the ground before flying off. I don't want to ruin too much, but if you've never seen it, it's honestly amazing and exciting and stuff. And I'll just hit play. Okay, this is basically the approach to Mars. Because Mars has an atmosphere, you will experience re-entry heat. So you've got to pack a heat shield with you. Okay, next comes the parachute, like I described. This parachute gets it down to slower than the speed of sound. So it doesn't do nothing. But Mars' atmosphere is very, very thin, only about a hundredth of Earth's thickness. So it's not going to be enough to slow you down all the way. Oh, wait, my mistake. This is Spirit and Opportunity. Even more bonkers than the sky crane was this, where they took Kevlar balloons and let the probe bounce along the surface until it finally settled to a stop. It's really kind of amazing, and even more amazing when it finally settled, it actually landed upright. We had obviously plans for if it didn't, but it was one of the bonkers ways that we chose to solve the problem. I'm sorry, I thought I had Curiosity here, which used a sky crane to get all the way down, instead of rockets just to slow it down to the point where the balloons would work. But obviously, once it got down to that point, it could start to unfold itself. The test vehicle for this kind of technology used a probe that was only about the size of a toaster oven. And Spirit and Opportunity were much bigger than that. They used the same landing system, though, so they had to have a whole elaborate system of getting the probe to unfold itself before it could even think about being operational. It's really kind of amazing that this worked at all, I'll be honest with you. We put the camera on a mast so we could see what it would look like from a human's point of view. Get the camera up there on a big old neck. These things were designed to work for 90 days, and they continued to work for years and years. Obviously, they're some of the most fantastically engineered space probes that NASA has yet created. They also started to hint at the subsurface water that a lander later confirmed, and as well as the deposits of where water used to be. And Curiosity, which I mentioned before, our latest probe, has been very exciting in that regard, because it's been finding not only confirmation that there were deposits there, but they've been finding some isotopes of oxygen in the deposits that are consistent with oxygen left behind by microbial mats way back in Earth's history, the fossilized remains. Now, we don't know for sure that this means life. It could be that there's some much more mundane chemical process at work, or some operation on Mars that just doesn't happen here on Earth. But it's exciting. It's unexpected. And it's one piece of data. If it turns out that there is life on Mars, then we'll eventually get lots of pieces of data, and they'll all point to that conclusion. But we have to start somewhere. And right now, we're still very much in the process of gathering information and trying to figure out what it indicates. If you're going to land on get to something much further away, though, and you've got time, something that we have developed recently is called an ion thruster. If you're a Star Wars geek, you probably know that TIE in TIE Fighter stands for Twin Ion Engine. Ion just sounds really nifty, So it's something that science fiction writers can seize on. But an ion engine is a real thing. It turns out that you can put charged particles in a container and then sling them out with magnets at very high speeds. And because you can control the fuel so very, very precisely, you can keep your rocket on for long periods of time. And you can basically change your velocity a whole lot if you're willing to be patient. This was what the Dawn probe used back when it tried to visit a couple of asteroids in the solar system. It actually parked in orbit around 2 different asteroids. We've had space probes visit more than one body before, but they've always flown by. Using these ion engines, they could actually keep the engine on for months at a time and just slowly spiral their way out to their destinations. If you're going to land on things like this, that's tricky again, because the gravity of asteroids and comets is so very, very feeble and very, very light. We've actually managed to do it, though. You probably remember the Rosetta mission. The European Space Agency had created a lander to land on a comet. And again, this wasn't easy because that gravity is so very, very light. The Japanese had tried it before with a probe called Hayabusa, and it turned out that they sent the message to go release the rover just as Hayabusa was making some correctional maneuvers in its orbit. And even those tiny little correctional maneuvers were enough to take the rover and fling it off into interplanetary space, never to be seen again. When Rosetta landed its lander on a comet, the lander was called Philae, it didn't so much power it down using rockets or anything like that. The gravity was too light. It just kind of let go of it, basically, and let the gravity gently float it down to the surface. They had hoped to use screws and harpoons to fasten it to the surface. It turns out that the motors that they were planning to use for that used an energy source that evaporated while the lander was on its way. And the lander ended up skittering across the surface and finally coming to rest under a cliff. Landing on comets and asteroids is still kind of fiercely difficult, and something we're still kind of learning how to do precisely. Even when I say that Japan planned to put a rover on an asteroid, calling it a rover is a little bit generous. It was more like a coffee can with a weight that could be flung around on the inside, and it would fling itself off the surface and then slowly settle back down again with these short little hops. That's as close as they got to a rover. Space basically offers all kinds of challenges once you're interested in trying to meet up with the surface gently. And that's all landing is. So we're still trying to figure out new and clever ways to do it. And hey, maybe somebody out there has an idea that will just be the killer app, as it were, the thing that allows us to do it in ways that we never dreamed of and allows us to visit more places much more efficiently than we thought. Anyway, if you want to get in contact with me, I'll put my email address and my cell phone number up there. If you use my cell phone, please be gentle. But I will try to answer any questions or find the answer for you if I can't answer it myself. If you've still got burning questions about how we get from point A to point B, and of course, there's the chat. So if you have any questions in there, please feel free to let me know. Thank you very much. And that's basically the basics of how we get around in the solar system.
So cool. So we have a couple questions. So let me get to them. We have a question here. So if you're on Earth and you're looking out and you can see Venus and Jupiter and they're pretty bright. If you were on Mars, would Venus be dimmer and Jupiter be brighter? Or would you? Okay. And would you even be able to see them because of the sandstorms?
Oh, well, sandstorms are periodic. So it's not that the planet is perpetually covered in a constant sandstorm. But you would be able to see Jupiter, as you say, more brightly on Mars, assuming that you are closer to it. You're in a part of Mars's orbit where you're closer to it than Jupiter. Because, again, not only does Mars get closer to Jupiter than Earth does, it also gets further away. Right? So you would see, if you're in the part of Mars's orbit that gets closer to Jupiter than Earth ever does, then yes, Jupiter would be brighter and Venus would be dimmer. Mars never gets as close to Venus as Earth does. So Venus would be dimmer. You would be able to see Earth as a point of light in the sky. And we have photos from rovers that have taken pictures of Earth from the surface of Mars. It's just zoom in with a little mini telescope, and you can actually see distinct points of light as the Earth and the Moon, which is really kind of neat.
That is cool.
A little bit humbling.
See that you can see the Moon.
I'm not sure that you could pick it out with the naked eye.
Yeah, that's really cool.
But
I know that there was the Voyager took that picture of the Earth. There was that pale blue dot that was, so if y'all have a chance, Carl Sagan wrote about that it's a really powerful image.
It really is. Something to note too is that from Mars's point of view, because Earth is closer into the sun than Mars is, Earth would be a morning and evening star on Jupiter, the way Venus is here on Earth, meaning that it would basically rise a little bit before the sun or set a little bit after. It would also be fairly bright because Earth's clouds and oceans reflect light really, really well. So I tend to think it would be kind of pretty.
Yeah, that's what I like to think so. So Buxton had a question. They have a game called Universe Sandbox. And is it possible to simulate? Okay, good.
I have that game. I love that game.
Okay. Is it possible to simulate the slingshot effect with Jupiter in that game?
Ooh, I don't know. I'll be honest with you. I haven't done. I've basically thrown planets at each other and made black holes and done all kinds of bizarre things with solar system bodies. I haven't done a whole lot with spacecraft. I mostly do that in Kerbal Space Program. And Kerbal Space Program, absolutely, you can set up slingshot effects.
Well, how do you? If you tell us how to spell that, Skelly can put a link to it in the chat.
Oh, Kerbal Space Program?
Yeah.
Okay. Well, their website is kerbal-spaceprogram.com, and I'll tell you how to spell that. Kerbal is Kerbal.
Okay,
and
awesome.
Space Program is what you'd expect. It's all one word, kerbal-spaceprogram.com.
Okay.
They have wonderful sales every once in a while, and I think you can get it for under $9 now. But basically, you slap rockets together with the complexity of Legos. Just make sure you have a capsule and a fuel tank and a rocket engine, and off you go. And you can. It uses physics, right? So you can dream up whatever path you want to take in the solar system and figure out how to get there. And if you manage to do it, it's because you learned something. The game doesn't make itself easy for you. So honestly, when you do something like land on the moon for the first time successfully, it feels like a triumph. My heart was in my throat the first time I did it because the ground seemed to be coming up way too fast. But it's a lot of fun, and I highly recommend it. But yeah,
that sounds good.
There.
That's really neat. All right, so that's a great recommendation. Okay, Carol has a question. What do you think is the largest problem in space travel?
Largest problem? Patience. honestly. Our human brains are not very well wired for long stretches of time where nothing happens and then having to pay attention. And that's basically what space travel is, because there's the distances we're talking about are enormous. When you're communicating, when you go over the recordings of the Apollo astronauts when they were on their way to the moon and back, you can actually hear the delay a little bit in the communications back and forth. It sounds like a 1.5 to 2 second delay between question and response. But if you're talking about going interplanetary, now you're talking about minutes of delay between question and response. So the distances are big. If you're flying from point A to point B, if you're, it basically turn on the engines and try to make sure your tin can keeps you alive for 9 months while you don't do anything. And then when you get to your destination, hurry up and make sure you fly the thing properly and land softly and all the nerve-wracking stuff associated with that, So I think the biggest challenge, honestly, is just being patient, surviving in between the few minutes of terror on either end, so that you can think well about what to do. And you have to think well because often things behave in space in a way that's different from the way we expect from our experience here on Earth. And you really have to think differently and be sure you do the right thing at the right time, or it doesn't work. So that's my quick answer. And anything that can be done to mitigate that patience, like better rocket engines or whatever, would probably solve a lot of problems. There are a lot of problems, don't get me wrong. I could also add in things like, how do we make good systems to keep people alive for long stretches of time and so on. But all of that would be much easier to solve if we could get there faster.
Absolutely. All right, Thomas has a question. How many gravity assists did New Horizons need to get to Pluto?
Well, New Horizons only used one, which is kind of unusual, I'll admit. It only used Jupiter to get to Pluto and beyond. It's still well on its way out there. It took a picture of a Kuiper belt object. I don't know if you remember that or not, called Ultima Thule, which is the most distant object in the solar system ever photographed. But we just shot it out real quick, small probe, big rocket, to get it out to Jupiter in a hurry, and then used Jupiter to give it that extra boost of speed it needed to get to Pluto and beyond. And that was it.
Cool. And Sean wants to know if we've discovered evidence of life on Mars.
Well, we have a lot of hints, honestly. This oxygen isotope that I was talking about, basically atoms come in different weights, and you can tell based on the weights of atoms that you have something about its history. And it doesn't tell you absolutely this oxygen came from life, but it's consistent with that. It matches that. It might match something else. We also know that there's water that collected on Mars. We have found traces of methane in the atmosphere, and some life forms here on Earth produce methane. We don't know where that's coming from, and that was kind of mysterious for a while. Is it life? Is it geologic activity? Because volcanoes can produce methane too, but we don't think the volcanoes on Mars produce methane anymore. We think they're extinct. So where is it coming from? We still don't know exactly.
Is it constantly replenished?
Yes. Okay. That is another tricky thing too. And that's a very good point, because Mars' atmosphere is so thin, ultraviolet light from the sun can penetrate right through, and any methane that is formed on Mars, if it's not constantly replenished, should disappear in a few centuries. Mars has been around a lot longer than that. So something is replenishing it.
So
we just don't know what. Yeah, it is interesting. And again, none of this is proof. But if we get enough little pieces of evidence that all point in the same direction, we're not there yet. But if that evidence is there, I really hope we find it, And one of the things,
it's cows.
Yeah. Actually, it turns out that the amount of methane being produced is roughly equivalent to the methane produced by one cow. And it was a joke for a while at JPL. Well, we just have to find the cow, So who knows? It's really kind of weird and mysterious. And I hope we find the answer. One of the things that Curiosity is doing is collecting soil samples in places where we think if there is life on Mars, it's likely to be here. And it's collecting those samples and putting them in place for a collection mission to be flown in 2026, I believe, to go scoop them up and bring them back here, because the laboratories we have here on Earth are way better than anything we can pack on a space probe. So if there is life on Mars, maybe we'll find it in 2026.
I hope so. I want to solve the mystery.
Yeah, it would be mind blowing. I mean,
I know. Oh my gosh, right?
Yeah.
Can you imagine? So Matthew wants to know, when you're traveling through space, are you relative to Earth or something else?
You can pick. Honestly, that is the what you've hit on there is the beginning of Einstein. And I don't want to scare you away from it by answering that question, but he basically figured out when you describe travel, you have to describe it relative to something. That's why we call it relativity. And there's no such thing as absolute motion. There's no such thing as being perfectly still in space. You can be perfectly still compared to that thing over there, be that the sun or the Earth or whatever you want to pick. But there's no way to know that you are perfectly still in space, as if there's some kind of background in space that you're perfectly still with respect to. So to answer your question, you get to pick. Usually, if you've got a landing mission, for example, they'll do exactly that. During launch and prior to leaving the Earth's environment, we'll describe motion of the rocket relative to the Earth. While it's flying on its way to Mars, we'll describe motion relative to the sun. And when we're going through landing operations, we'll describe motion relative to Mars. So we would love to have one system that works for everything. And it's been suggested that if we could add up enough of the spinning systems in the solar system, we could create a coordinate system out of that would work across the entire thing. But we don't know enough yet. We're still, our error in measuring these things still leads to an error in the coordinates of a few degrees here and there. So we're working on it. But the answer is, if you find something convenient, use that.
What a wonderful question. Thank you.
Yeah,
Matthew.
it is. It is
cool
very,
answer.
very insightful. Like I said, it was Einstein who figured that out. That is phenomenally insightful.
So DJB has a question. What was the fuel rocket system for Webb, and what does it use to remain at Lagrange 2? Sorry, Lagrange.
Lagrange. Yeah, he was French.
I was born in Lagrange, in a town called Lagrange, so sorry.
Hey, no worries at all. That's a very good question. I'd have to look that up, to be completely honest with you. It's very common.
Just to say, we have some Webb. We have one of the scientists working on Webb is speaking on Saturday. So
fantastic!
You should definitely come to that talk and ask that question. Definitely.
It was an Ariane 5 rocket, and they used liquid oxygen and something else. I don't know. Very common fuels to combine with liquid oxygen are liquid hydrogen and what they call RP1, which is a special kind of kerosene. I'd strongly suspect that Ariane 5 probably used that. It's also very common when you're talking about small thrusters, like James Webb would use, to use stuff called hydrazine. It's a monopropellant that basically reacts when it's exposed to vacuum. It expands rapidly there. It's not explosive on its own. So that makes it, much safer to store and deal with. And unfortunately, it's toxic to life, but, hey, you have to make trade-offs with these things. Just be very, very careful when you handle it. So if I had to guess, that's what I would guess. But keep in mind that it is a guess. I don't know for sure.
Okay.
How is it staying there? It is using little pieces of thrust too. L2, which is a stable Lagrange, an unstable, I should say, Lagrange point beyond the moon. You can orbit it, but it's like balancing a pencil on its point. You won't stay there unless you're perfectly balanced. We're not perfect at anything. We're humans and we mess up from time to time. So we packed fuel there to make sure it would stay in its orbit and stay close to L2 for as long as possible. Sorry to keep rambling there. Please
no, that's cool. So Kay has a question. Where do probes go after they pass Neptune?
Further out. I know that's not much of a question, but we don't have, presumably if you're going out towards Neptune, you've gotten slung out there by Jupiter already, and you're probably going to keep right on going. The Voyager 1 and Voyager 2 actually visited Neptune. Voyager 1 didn't. Voyager 2 visited Neptune, and it just kept right on going. And right now it's about 12 light hours out, which means that it takes a full day for us to get for that whole question response system to go back and forth. And even then, it's only just left what some consider to be the boundary of the solar system. It's only just started flying an interstellar voyage, if you want to call it that. Again, the spaces we're talking about are enormous. So where do they go if they go past Neptune? Just further and further away from the sun. They go into galactic orbit, I guess would be the answer.
That's cool. So Ethan wants to know, can you watch Netflix in space?
You know, that is an awesome question. No, it seriously is. Netflix is on the internet, and the internet has a system of communicating back and forth so that the sender can be sure that the receiver is getting the information that it's sending out. If the delay there is too long, then it breaks. And the delay is fine for distances across the surface of the Earth, but it would break down if you tried to move out to the moon, where you're talking about distances, delays of more than a second. That said, there are different methods of communicating back and forth. There's the internet uses two different communication methods to send information. TCP is what you usually get if you're sending files to make sure, absolutely sure that the files are the same that you send out. UDP is what you send out with things like streaming information, and the server cares a lot less about whether you're getting exactly what it sends out. If I had to guess, and again, this is a guess, Netflix uses UDP to send out its video streaming information. So I guess potentially, if you could figure out how to get the command to start sending the streaming movie out, it'd be fine doing that, and it wouldn't care whether you got the individual packets or not. It would just sort of send out whatever it could and hope that you got it. But you wouldn't be able to switch back and forth between different programs that you wanted. You'd have to have that all arranged by somebody sitting on the surface. So you could watch a movie if someone arranged it for you from the surface, is what I'm guessing. And hey, look, Netflix has its trade secrets. I'm just doing this based on networking information because, you know, I'm an electrical engineer by education, and I had to learn this stuff. And I do software engineering as a trade, so I ended up picking up a lot of network garbage. But yeah, that's an awfully good question. Some have said there is active study right now about figuring out how to expand the internet if people decide to set up a permanent station on the moon or a permanent station on Mars. And one of the suggestions is basically that we have two internets, and every once in a while they communicate back and forth and ask, have I missed anything? Send me everything you've got from Tuesday to Saturday. And they update each other over long stretches of time. It's a great question because communication lag is a stupid thing. Man, we talked about patience. It's a difficult problem. And that was probably more detail than you wanted, but there it is.
It was a good question.
Yeah, seriously. Like these people come up with amazing questions.
I know. That's why I love astronomy days so much. Okay, so I have one last question.
Yeah, and I'll try to answer questions faster.
What would happen if we launched a cow to the moon or Mars?
A cow to the moon? I can't imagine the cow would be very happy.
Be cooped up for a long time.
Yeah, it'd be stuck inside a tin can for a while, and I don't know of any tests that have tried to put a cow in a tin can and see what it does. But I don't think it would be very happy about it. I don't know how it would adapt to zero gravity. My goodness. How do you milk a cow in zero gravity? But
vacuum
yes.
suction.
Yeah, you'd have to use some kind of pump system, wouldn't you? But wow, what a question! Holy cow, so to speak. I don't know exactly, but there's a whole lot of questions that have to be answered.
But I would think that you would need a lot of like support equipment to go with it, right?
Yeah.
So you would need like life support for such a large animal.
Yeah. And not to be too crude,
and food,
waste collection. I mean, is
all
there
that,
a cow
all
diaper
that
big
methane?
enough? Yeah. Oh, the methane. There we go. We're back to the methane. This whole thing has come full circle. It's amazing.
All right. What a great place to stop. Full circle. Well, Matt, this has been absolutely delightful. Thank you so much for joining us today.
Oh, thank you for having me.
Skelly's put a bunch of links for our upcoming programs and our recorded programs. So if you missed any, you can watch the recordings, and we have lots more. We are not even halfway through Astronomy Days yet. So exciting stuff. So thank you very much. And I'm going to stop your share, and I'm going to share mine.
Alrighty.
Because I want to show y'all that we have t-shirts. We have awesome Venus shirts this year for Astronomy Days, and hoodies. So if you want a shirt, you just go to store.naturalsciences.org, or if you're in town, you can go down to the museum and go to the store and grab one. Thank you so much, Matt, for doing this. And I want to thank our sponsors, North Carolina Space Grant and Pepsi. And I want to thank our members. So if you are a museum member, thank you so much. Your membership makes programs like Astronomy Days possible. And if you are not yet a member, you should consider joining, because your membership, again, helps us put on programs like this, and you get cool discounts and lots of other perks. So everyone, thank you so much. Have a wonderful night, and I will see you tomorrow. Bye-bye.